Okay, today the metric-driven methodology for firmware verification in simulation and emulation environment. Abstract. Contemporary embedded system has more and more firmware included directly on the die. Verifying it thoroughly before the final delivery is sometimes challenging due to lack of appropriate verification tools. An in-house built tool using common SystemVerilog and mostly free of the charge technology, Perl, HTML, CSS, JavaScript, demonstrate a metric-driven method for the firmware verification process that is easily reusable and other embedded verification environment. Section 1, the introduction. A typical embedded system consists of one or more processing units, usually the ARM core or other lightweight Cortex, which control the system. More and more the functionalities of such a device is actually stored in each firmware, which implement a higher level of controllability of the device, while at the same time they extend its flexibility using more complex algorithms and patterns available at a higher score, higher software level, using standard programming languages like C. Such a firmware inevitable because a part of the design and has to be extensively verified along with the hardware. Figure 1. Typical embedded system. During the verification process, it is important to thoroughly verify this. Now, crucial component of the design in order to avoid any gaps in the verification process. A common metric for doing this is having the complete software coverage of the firmware performed in order to confirm that every use case scenario has been verified. Here is presented a simple, reusable, and a tool independent solution based on SystemVerilog, Perl, and common HTML, CSS, and JavaScript. Internet technologies which has been successfully used in a couple of commercial embedded projects based on a low-power ARM Cortex. A lightweight variant of this approach may be implemented in the FPGA verification as well. Section 2, existing solutions. Currently, the functional and code coverage of digital design verification, which is fairly well supported by a number of EDA tools. The software coverage usually depends on custom extensions and their implementation especially required for some parts of the firmware, bootcode, test functions, where standard firmware coverage tools are not available yet. Although it is possible to use the built-in SystemVerilog support, sample, cover point, cover guru, for performing coverage on software code as well. In practice, it is fairly inefficient and requires the data verification engineers possess a fair amount of the software, hardware skills regarding the target system just to be able to identify the missing software component. Figure 2 is the detail from a typical coverage report of a firmware generated using standard coverage tools. Figure 2, typical coverage report. Detail from a custom coverage report custom for firmware. On the right are the successive address associated with the function DAFW main_main, showing that an instruction or data element at the address is covered or not. It is obvious that a verification engineer has incomplete and quite cryptic bits of low information regarding the executed code. The basic motivation is to provide a set of custom-built tools that may drastically improve the verification process and make it more accessible to the wider range of verification engineers. Section 3, implementation. The implementation is done in a low-power system-on-chip SoC embedded design with multiple ARM Cortex M0 plus cores using a standard cadence verification environment based around the SystemVerilog tool. Each core has its own memory space firmware amplifiers attached to it. Firstly, basic tool requirements were identified in order to estimate their feasibility against the simulation environment and potential constraining flows. Secondly, a set of tools has been chosen with their availability, cost, and productivity in mind. Several potential critical points in the flow had been tested before the actual implementation was started. Basics of software coverage. Generally speaking, tracking the flow of the program requires two major components to be monitored. In the program counters register, PC, it directly follows the program execution if an instruction address appears in the PC. It means it is being executed. Remark: if there is no speculative execution, then the industry may be dropped eventually. The dedicated instruction or a general purpose database AHB represents a high performance bus in the ARM. Not all the code contains executable instruction. A part of it consists of different data as well, so they have to be taken into account and covered as well. Their address locations do not appear in the PC and therefore would not register as covered. Since all the components of the design are usually available to the simulation environment, it is easy to connect these two to a single SystemVerilog interface of our code coverage monitor. The system is sketched in Figure 2. Figure 3. Monitor interfaces and a point of connection. Data flow from the tracked point to the monitor, and their temporary storage in the address area are marked with the red arrows at the end of the simulation. The collected data are saved as a custom coverage file. Notice that in a case of a multi-core design, the bus and PC of each core need to be tracked separately in order to distinguish between the different firmwares. Besides tracking addresses, it has also be registers which core and/or memory space it is dedicated to. B. Additional design requirements. The PC and the AHB must be accessible to the simulation environment. That is, they must be readable from the SystemVerilog-based test bench. However, some systems have their specifics, and the tool shall be aware of these deviations from the commonly accepted behavior. For example, in an ARM-based system, the actual value of the PC pointer location of 4 bytes above the memory address of the instruction currently being executed. Furthermore, in gate-level simulation, GLS, some bits of a register and bus might be omitted due to the optimization during the synthesis phase. So instead of accessing the PC register directly, it is considerably more efficient to use exposed values of a rather specialized DWT IAEX bus of the Cortex itself. It points to the address of the actual instruction, and it works just fine in the GLS as well. C. Collecting coverage data. The addresses being accessed during a simulation run are collected in a SystemVerilog associative array in the code coverage monitor component. The reason for using associative arrays in a tool arrays is to allow a full range, 32-bit, of the memory addresses to be tracked. Each element in the array associated with an address has 3 counters: read accesses, how many read requests were performed from the address; write access, how many write requests were performed to be address; executed, how many times the instruction at the address has been executed. The accessed executed addresses are collected concurrently from the AHB and PC, and new entries are added to the array if the address has not been registered before. Each new and read or write transaction on AHB will increase the appropriate read or write access counter, while any new value of the PC will increase the executed counter for that address. The address resolution should be at least 2 bytes since 16-bit ARM thumb instruction set is used. This way, the monitor is to distinguish particular 16 to the 32-bit instructions as well as accesses to the 16 or 32-bit data. The resolution of data access can be extended even further to the byte level, but it is generally not required for this task. D. Generating collected output. At the end of a test case run, the collected addresses with the number of read, write, executed accesses are saved to the directory of the test case in a simple texture format. The disk space consumption is not critical, so we have chosen the following texture format depicted in Figure 4. The Figure 4 custom coverage file format. Each access to address is presented through its offset in a predefined memory block which has its base address, and then the number of read access after the R character, the number of write accesses after W, and the final number of the execution after X. Notice that the memory block may be associated with a different memory space underscore, so this information has to be provided. C#:N shown in Figure 4 along with the addresses covered in order to allow multiple memory spaces. E. Collecting and connecting the collected data. When the coverage option is enabled in simulation, which each test case run, even in emulation, and each run directly collected the required data within the custom coverage file previously described. Collecting all the data created in the regression and the later processing is performed using a custom Perl script with a number of features which should generate a coverage report at the end. But it is not unusual that an embedded device has more than one part of the firmware, functionally API bootstrap test functions. Usually they are internally distributed in the executable and the linkable format, ELF, files which are naturally the major and the obligatory input to the script containing all relevant information related to the firmware whose functionality is verified. Once these ELF files are disassembled to the texture format using Firmware for object dump command line tools and eventually cached to the speed of the process. Each generated file is parsed line by line in the different sections, functions, individual instruction and data associated to a function are identified, are stored in an appropriate data structure for later processing. A sample from a raw output of the from ELF tool is given in Figure 5. Figure 5 examples of disassembled ELF file, raw texture format, function main disassembled with each interleaved source shown. The first firmware data are usually stored in the form of the associative arrays which form a tree structure at ELF section and function levels, thus allowing quick looking up based on their names. Finally, each function node in this tree contains an associative array of instruction and their data elements associated with their physical addresses, so they are uniquely identified for that memory space and core. Each ELF section function instruction node in this tree also contains other parameters, memory start and number of instruction and data, in order to ease their later processing. Another functionality of the script is correct previously generated firmware coverage either in a single run, simulation or emulation. Parsing the custom coverage files in the format given in Figure 4 from each test directory is straightforward, and corrected addresses with a number of different read and write and executed address to each address by different test cases is easily performed. Matching the overall number of the accesses to an address of a memory space core and with an instruction or data element from the associative disassembled ELF file shows whether the instruction and data have been covered by a set of the test cases. So nevertheless, this is optional. So an ELF file alone may be inspected in this visual element environment without coverage information. Finally, all the collected data are finally saved in the final HTML report. A reasonable amount of care should be taken here since a large quantity of data may affect final HTML report performance. For example, the HTML format has a lot of redundant data in the format specification, so it would make a generated report file enormous. So providing only raw data along with the dynamically created HTML to graphically represent the data ensure that both memory footprint of the application and final user experience are quite acceptable. F. Graphical report. The final report may be presented in raw text form, no raw text form readable in any text editor. Nevertheless, to increase the usability of a generated report even further, it's better to represent the collected data in a more readable form. Using a common and or present HTML and CSS with additional scripting is a good choice. The tools are widely available free of charge and extendable further with good overall support. The presented graphical interface shown in Figure 6 can represent the corrected data at several levels. Figure 6 is generated report and its graphical interface as rendered in an internet browser. The disclaimer: the code shown here is for demo purpose only. It does not reflect the actual implementation. So it shows the coverage statistics and the number of accesses at ELF and ELF section and the function and instruction data levels. One may easily track the assembler's code against the C language source code, leaving the choice of finding verification coverage gaps and related non-executed code to a lower level and verification engineers of a higher level firmware designer. Note that the almost all data available from an ELF file are preserved in this graphical form, but displayed in a more acceptable manner and just one or two mouse clicks away. For example, incomplete less than 100% instruction or data coverage of function from the list will be marked red, so it may further inspect by the clicking the link which opens the details report for unclog or code in a sub-window. Labels in the assembly code are also links and enhanced makes navigation through it with ease. The detailed report contains the actual instruction codes in addressing ascending direction. Their assembler mnemonics and corresponding C sources followed with their originating files and line numbers. In access columns, the array given the number of reads and or the write for an data element or the number of execution of an instruction. The instruction datum line with expected access will be marked red. For example, the instruction was only read and did not executed, meaning it is not properly covered by the battery of the test. It is also straightforward clear which part of code was not accessed. Thus, the following verification engineers to cover the kernel as well. They encountered implementation issues. Despite of doing a recent amount of research using the different software components, several obstacles during its development has been encountered in range and dealing with minor differences in format of the C source code delivered by different software developers involved in the project, to browser incompatibilities in the implementing the HTML, CSS standards along with the rendering incapabilities of servers, for instance. H is additional features. The executable code and data are associated with their appropriate addresses in the memory map of the core. Since the memory addresses being tracked by are not associated with the memories only. So one may also track its addresses to all addresses in the memory map. For example, one data track is whether all registers of a memory module has been accessed, the type of access, read and write, as well as the number of access in a set of the test or regression. The right way implementation in FPGA. As an embedded system is usually verified on an FPGA-based test board as well, while the method introduced way faster simulation and additional availability of some common software tools in the software development team. It is still lack of coverage information due to the nature of verification method itself. Nevertheless, it is possible to implement a lightweight software coverage verification component for the FPGA platform as well, at little or no cost at all. An FPGA platform usually has a built-in RAM and the random access memory blocks available for the synthesizing and emulating different memory models, RAM or ROM or NVRAM. Only one of them is made connected to a rather simple custom controller, which is connected to PC, IAEX port, and AHB. Tracked values on these buses is done in a similar fashion are already described in the design verification, where one may associate one bit of the memory to a 16-bit instruction or data element to mark whether the address has been accessed or not. For a 128 kilobyte firmware, an 8 kilobyte block RAM is enough to provide coverage on a firmware instruction data. This is an acceptable trade-off between the required FPGA resources, simplicity of the implementation, and finally usefulness of the corrected coverage. For test regression, the contents of the RAM should be preserved between the different test cases, so that at the end, the collected data and the block RAM may be easily acquired through a general debugging interface and analyzing later in the same tool. The section 4 is the conclusion. The custom-made software tool is managing firmware coverage, relatively inexpensive tool developed for the refer to a section implemented code, the complexity below, but it justified the investment shortly after through its new value added to a set of the existing tools. It allows the easy identification of coverage gaps during the firmware verification available to a wide range of engineers involved in the verification process, while making it metric-driven. So to rely on each development of the freely available on cross-platform tools and technologies, making a fully platform independent, regardless of the simulation environment or final report consumer. The flexibility of each realization allows many further improvement. Some of them are listed in the section further improvement below. J. Implementation code complexity. For creating a tool like this one, an estimated effort is summarized in Table 1. Table 1 is the estimated development cost of the particular tool component. Of course, these numbers are quite approximate and it depends on many factors like used coding style, a list of functionalities implemented, and etc. K. Archived result and limitations. The exposed methodology has been used in 2 projects so far, covering the only specific firmware component in the simulation environment, where the targeted coverage was 95% to 100% depending on the component. Despite the ability of the tools to precisely handle software coverage, it's usually constrained only to a set of critical firmware components which have to be extensively verified. A typical firmware development process is usually based on a FPGA test board, which offer greater execution speed and a more comfortable environment to software developers. So it is natural and more efficient to do the full firmware coverage on the FPGA along with its development and software unit tests. Providing coverage in both environments additionally ensures that there is no loopholes in any environment, especially where the critical software components are tightly related to the hardware, requiring finer details of the design with the specific stimuli. Since all design elements, software and hardware, are accessible to the simulation environment, there is practically no limitation on other than the speed of a simulation. The load introduced to simulation environment is less than 1%, both in simulation performance and memory requirements. Nevertheless, for a firmware of modest size 128 kilobyte in the generated HTML report is about 226 megabyte in size, mostly dependent on whether the C source code is included or not. So it may impact the user experience of particular browsers. Further improvement. Color coding for improved code reliability and graphical analysis of multi-browser support switch from the proprietary from ELF to open source OBJ dump. Filtering and sorting the result in the report are amongst many people improvement of the tool that might take place in the future. The acknowledged and reference. Okay. Thank you for your time. Today I read this DVCon2016 paper in Europe, and a metric-driven methodology for firmware verification in simulation and emulation environment. Thank you for your time. See you next time.